section 4.2 Cofactor expansion and applications of the determinant. Okay. Okay. In this section, we will introduce a method to compute the determinant. Okay. And and also, we will see a formula to compute the inverse of a given matrix by using the determinant instead of Gauss-Jordan elimination. First, we introduce two definitions. One is a minor and the other one is a cofactor. First, suppose we have n by n matrix A like this, then if we delete the ith row of A and jth column of A, the matrix A, then we denote that n minus 1 by n minus 1 square matrix in this form. Okay? We delete the ith row and jth column, so it's a smaller matrix from the given one. And think about the determinant of that matrix, determinant of that submatrix, determinant of A, sub I, then J, deleted. We call this determinant Mij a minor of A, minor of the matrix A for the entry Aij. And the cofactor of the matrix A for Aij is defined as minus 1 to the I plus j times the minor. Okay, the determinant of A sub I and j. So, minor is a determinant, and cofactor, we have a sign in front of that minor. Okay, here, suppose we have a 3 by 3 matrix like this, then find the minor and cofactor of A for A11. Then we delete the minor, delete first row and first column, then we have a 2 by 2 matrix like this. Then determinant of this, which is 16, is the minor of A for A11 entry. Then cofactor of A for A11 is the product of the minor and the minus 1 to the Ij plus the addition of I and j, which is 1 plus 1. So this is going to be 1. So cofactor and minors are same in this case. But if we, okay, and adjoint matrix, let Aij be a cofactor of n by n matrix A for Aij, then the matrix transpose of Aij, which is a cofactors, is called an adjoint matrix of A and denoted by adjoint of A like this. So adjoint of A is a transpose of a matrix which consists of the minors of the cofactors of matrix A. So cofactor of A for 1 entries here, cofactor of A for 1, 2 entries here, cofactor of 1 n entries here, which forms the first row of the matrix, and like the others. Then take a transpose. So it is a transpose of cofactor of A on i's and j's entries. So if you write it in this way, then A11, A12, and A1n goes. This forms the first row, and A21, 22, 2n forms the second the column, and N1, N2, Nn forms not row. It forms the column in the adjoint matrix of A. So with those definitions, we can always find the adjoint matrix of A for a given matrix. So find the adjoint of A of the following matrix. Then we can find A11, which is a determinant of 2 by 2 matrix, times the sign here. A12, which is the determinant of 1, 2 here. So we delete first row and second column. Then we have 5, 2, 1, minus 3, and determinant of that times minus 1 to the 1 plus 2, which is minus. So A13, A21, A 3, 3, so we can find 9 cofactors. From those 9 cofactors, we can form a n by n matrix, 3 by 3 matrix with those on the same place, then take a transpose which forms a adjoint matrix like this. Okay. So similarly, if we define a matrix like this and just give a command to find the adjoint matrix of A, then you will see, you will have the same matrix like this. Cofactor expansion. Suppose we have a 3 by 3 matrix like this. Then determinant of A can be written in this way, isn't it? 3 by 3 matrix, we have a 3 positive terms and 3 negative terms like this. If we combine it in this way, then we see this is the cofactor of A11, and this is a cofactor of the matrix A for A 2-1 entry, and this is the cofactor of A 3-1 entries like this. So this can be written in this way. So we call this is the cofactor expansion of the matrix A along the first column, because first 1, 1, 1, 1, 2, 1, 3, 1. So first column are used in this way. This is known as a cofactor expansion of A along the first column. Okay. So, but this concept not only works for 3 by 3 matrix, it works for any size of the matrix. It's not only work on the first column, it also works for the second column and third column, and also it works for the first row, second row, and third row, and nth row as well. So, this is a very important tool to calculate the determinant of a small size matrix. Another important, interesting fact is this. For any 3 by 3 matrix A, the following identity holds. Just try to multiply A times adjoint of A. Just try to multiply. Then what we're going to see? The first entry is going to be A11 plus capital A11 plus little a12 times capital A12, and plus little a13 times capital A13. This is it, which is a determinant of the matrix A. But you will easily see the other terms. So main diagonals forms like that, but off diagonals, the off diagonal the entries will be 0 for any matrix, like you see in here. From this cofactor expansion, you will see the main diagonal entries are determinant of A, but all the off diagonal entries are 0. So this can be written as a determinant of A times identity matrix. Okay, so you see, because you will see this work for any matrix. This is okay. Important thing is this not only works for 3 by 3 matrix, it works for any size of the matrices. Okay. So just let's check it. The matrix A is a 3 by 3 matrix of which we had before. Then consider find the determinant of A. Then it's minus 94. Then try to find the A times adjoint of A. Then you will see that's going to be like that. Looks like this, which is the determinant of A times identity matrix. If you change the matrix of any size here, you will see always the A times adjoint of A is the determinant of A times identity. Laplace found this property, and he proved it, and the proof is quite simple. But you will see. So from those observations, Laplace wrote a theorem like this, which now is called the Laplace cofactor expansion. For any size of matrix A, the following hold. Determinant of A is like this. It's a cofactor expansion along the ice law. 요것 좀. Okay, and the determinant of it can be found by the cofactor expansion along the J's column for any columns, any rows. Okay. So yeah, from here, as I mentioned, if a matrix has a row or column which has several zeros, then the sum of these terms is going to be a zero. So the computation of a determinant of a given matrix will be easily obtained by using this cofactor expansion property. We'll see it. Yeah. So as I mentioned here, it is advantageous to use the cofactor expansion along the row or column which has many zeros. Let's see one example. It's 4x4 matrix like this. Then from this matrix, if we do the Gaussian elimination, and so you make it a little simpler, we may exchange the we do some Gaussian elimination to have this like that. Then finding the determinant of this matrix is much easier than the given one, because it has a column which has 3 zeros here. If we do the cofactor expansion on the first column, the determinant of A is just finding delete this first column and second row, and we have a 3x3 matrix. So finding the determinant of this 4x4 matrix is almost same as finding the determinant of this small size matrix, which is minus 18. So that's the key idea. Okay, and also from this, from the observation that we had, A times adjoint of A is a determinant of A times identity. From there, okay, as I proved on the board, the A times adjoint of A is a determinant of A times the identity matrix. So if you multiply A inverse when A inverse does exist, then multiply A inverse on both sides, then divide the both sides by determinant of A, then we get this formula, which says inverse of a given matrix can be easily found if you do compute the determinant of A and adjoint of A, like what we did. So suppose we have a 3x3 matrix like this, then find the determinant of A and find the adjoint of A. Then 1 over determinant of A times adjoint of A is going to be this matrix. Then, and also we just find the inverse of the given matrix with this command, then you will have an inverse matrix of the given matrix like that. As you see, these two matrices are same. This works if whatever matrix you have on here, any size of matrix and any type of matrix. So there are you now learned another way to find the inverse of the given matrix. Okay. Any questions on section 4.2 cofactor expansion and finding the determinant by using the adjoint of A?